Hi, Farooq. How are you today? It's great to see you.
Nice to see you. Thank you, David, for hosting me today. I'm an analytical chemist by training. I did my PhD in chromatography with Charles Lucy at the University of Alberta. And then I came to the University of Texas. I did postdoc at a startup company where I learned a lot about stationary phase synthesis and packing science. And then I joined as a staff scientist at the University of Texas at Arlington. Um, Here, I'm more interested in signal processing and chemometric applications for chromatography, spectroscopy, and so on. So I got to know how the commercial aspects of chromatography as well. And this is where my interest in peak shapes originated. So I think we are going to talk about peak shapes today, right? So,
Absolutely. And I think it's a
mhm,
great topic for
right,
the audience for this podcast,
sure, sure.
undergraduate researchers, and then also people who have been doing chromatography for
That's true.
a long time.
That's true.
So, what does a good peak look like, and why is it important both in research and routine lab work?
That's a very good question because ideally you should get a pure bell-shaped curve, which is mathematically called a Gaussian curve or a Gaussian function. So it's your bell curve. Nothing unusual about it. It was known hundred of years ago. But it turns out that if you study chromatography in detail, theoretically the peak shape should be like a bell curve, right? And in reality, it's not. What you would like, you can have fat bell curve or you have a very narrow bell curve, right? So you would like to have a very narrow, sharp Gaussian, which helps you in integration of its area. You know where it is starting and where it is ending, right? And you can easily detect it with your eyes because eventually your eye is the thing which is going to tell you that here's the peak. I mean, software can tell you, but sometimes there are false flags as well that they can highlight small peaks as well. So that's what you want. Ideally, you will never get it, but you want to be near Gaussian, narrow, sharp peak.
Can you share examples of how you've spotted these issues and maybe what caused them?
Mhm. Coming to the real life problems, I think you will see non-Gaussian peaks, as we call it, right? So non-Gaussian means you can have a tail, decaying peak, or a front, which means a slow rise and a fast decay. But if you're doing good chromatography and your mobile phase and instrumentation are all optimized, you should see near Gaussian peaks. And how do you optimize them? It's just like asking what is the cause of a complex disease, right? Like, god forbid somebody has cancer, what is the cause? There's so many that it's high difficult to list. I would say there are dozens of causes for bad peak shapes, but you can classify broadly in the sense that you can say that there are thermodynamic reasons for bad peak shapes, there are kinetic reasons, and then there are fluid dynamic reasons, right? So thermodynamic reasons mean that you have injected a significant amount of mass of your analyte into the column, and there is no sorption capacity for your analyte. So it does not behave ideally, and you get bad distorted peak shapes. That's thermodynamic fronting and tailing. Kinetic tailing comes when you have multiple interactions of the analyte with your stationary phase. So some interactions may be holding the analyte and they're slowly coming off and from the column, and then you have a tail, right? The third reason, which majority of the users do not see, is that when you are manufacturing columns, I mean, there are a lot of academic labs, research labs, which they make their own stationary phases, and they have to pack it themselves as well, right? So in packing, what happens that when your bed structure is bad, your particles are not ideally distributed in a column. Some areas are tightly packed, some areas are loosely packed. Then your bed structure is not uniform anymore, and then you see fronting, tailing, split peaks. Sometimes we used to call it like a ballerina peaks, like they have an Eiffel Tower peaks. These are internal words, but that's what you'll see. So there are multiple causes, and it's a case to case basis. Should I discuss more causes as well?
Sure, absolutely.
Okay. So more causes when it comes to chemistry. These were physical reasons, right? Chemically, what happens at times that your analyte can also chelate. A majority of like if your molecule has hydroxyl groups, carboxylate groups, and amines in the same like molecular entity, they can form. chelates with the metal. And where's the metal coming from? Whole HPLC is made from metal, right? Because it has to withstand very high pressure. So you have frits, you have tubings, you have column material itself, and detectors are fine. But there you can see interaction. You can see massive tailing, especially if you have phosphates. And if you, I mean, remember old high school chemistry, phosphates love iron. And you have what do you have in HPLC? Like you have iron components and steel and so on. So it interacts very strongly. Phosphate groups interact very strongly with iron surfaces, oxidized iron surfaces, and sometimes you will never see them. And that's another extreme of peak shape. You never see it elute from the column. It's stuck there forever. So you need to wash the setup with a chelating agent, EDTA or something like that, and that will remove those analytes.
For students, numbers like tailing factor or asymmetry factor are everywhere and easily accessible. What can't these single values tell you about real peak shapes, and why should you look at the whole peak?
True. That's a very valid question because people have preferred these single valued numbers for assigning peak characteristics because they're easy, right? Everyone wants to have a simple calculation, take a pencil and a ruler, or use a computer software. All software have this measurement. They will tell you what's the tailing factor or asymmetry and so on. So people have been using it. But when you do high efficiency chromatography, then you start to see non-idealities. Then you need a full picture, right? For example, if I want to describe a person with a single number, just say David is 6 feet tall. It doesn't tell me anything else, right? You have a number. So single number, or describe a picture with a single pixel, it's not going to tell you the whole. So we have to look at the big picture when you're doing more complex research or you want to go deeper what is happening, especially when you're interested in narrow, when you want to produce narrow high efficiency peaks. You want to see where the non-ideality is coming from, and this is where you need to look at more advanced tests like which we developed, such as the Gaussian test or the derivative test and so on. We'll discuss about it later.
You touched on the common causes that lead to distorted or messy peaks a little bit
Right, right.
earlier. Could you
Yeah.
walk us through a memorable example where understanding the peak shape led to fixing a big problem?
So you know that chromatography has a commercial aspect as well, right? So when you modify silica surface, the next question is how to pack it in a narrow stainless steel cap tubing, right? So people have been studying this for more than 50 years, and it was considered trade secret. So if a company has some method or scientists know a certain method, they won't share it with others. They will think this is a proprietary information, we cannot share it, and so on. So this really, in my opinion, throttled the science of stationary phase synthesis, because people say, hey, if even if we synthesize it, how will we pack it? And it will take a lot of time, nobody knows how to pack them. So in my PhD and in my work at University of Texas at Arlington, I investigated how the science behind high pressure movement of suspensions in these tubings. Eventually, I came up with a qualitative rule, and I have not seen a single exception yet. I may not be boasting, but in 10 years, you can do simple tests, and that will save countless man hours, person hours, in terms of doing random hit and trial experiments. So what I came up with is that you have to use a suspension, right? You have to suspend your silica particles, then you pressurize it. It's a high pressure filtration. It's basically an engineering problem, right? Column packing. Right? So what happens is that if you use suspensions and if you look under a microscope and if they appear like grapes, all particles are sticking together, discard that suspension, that's not going to work. And if you see very finely like dispersed particles under a microscope, they're slow to settle and so on, but is where you proceed forward. And that eliminates completely the randomness or the hit and trial methodology. And that is the most critical factor I found experimentally. A lot of companies benefited from these tests. I mean, I got emails from Italy or other people, even from Pakistan. Somebody opened a company for packing columns, reading my articles, and they said that article was really helpful. So it saves a lot of time basically, and it eliminated the hit and trial aspect. With that, once we published that article, what happened is that other people also opened up. Other groups at University of North Carolina, especially Professor Jorgensen, published findings on how the capillaries pack, how narrow bore columns pack, how does the microstructure of the bed look like. They did very advanced microscopy and so on. And he also developed tests. Now I think the science is relatively more established, and anyone who's interested in making new station phases can now proceed with making their own columns, right? If they
Yeah,
follow the simple rule. Yeah.
it's critically important.
Mhm.
What simple steps could students take, or new analysts, I should say, if
Mhm.
they start to see or experience poor peak shapes in their experiments?
That's also a very valid question, and that's the most frequently asked question as well. That, oh, we are not seeing the instrument is behaving badly, and we are not seeing the like peak shape is a bad. So the trick is go back to the basics again. What you do is that you first isolate the problem by saying, is the problem coming from the HPLC column, or is it coming from the entire instrument, right? And the tests for both are easy. So you, since you, if you, somebody is doing chromatography, they must have multiple columns, and get a new column, open the box, and you'll see a quality control sheet. Every manufacturer shares a quality control sheet. They say analyze these molecules, and they should elute at a certain retention time. Should be the peak widths, and so on. Repeat that method on your instrument, and if your results are completely erratic, your retention times are off, there's a problem with the instrument because the separation column is new, right? Uh, but if that passes, you can take a sigh of relief and say your instrument is working perfectly because I can reproduce the results from the company, from the manufacturer, right? Then you can target, is your method the problem, is your column the problem, or maybe yourself. I mean, sometimes the operator is the problem as well. Like they made the wrong buffer. Sometimes they forgot to add a certain solvent. So I remember that one day somebody made a mobile phase, and then I saw on the HPS there were two layers. They mixed immiscible solvents, and they were trying to do chromatography with that. So mistakes happen. We are all humans, but this is how you should always do the benchmarking, and that's the easiest test I can suggest. Of course, method to method, analyte to analyte, there will be specific examples, and then you have to do research. But benchmarking is the easiest thing. Go back to the standard test suggested by the manufacturer. If the results are good, everything is good.
You touched on this briefly a little bit ago. You've proposed visual tests for
Mm,
analyzing peaks, and how could students use simple platforms or tools like Excel to
mhm.
investigate their own data and hopefully go beyond what the standard instrument software might show?
Okay. So my philosophy is that, like, when we write mathematical papers, like where we have a lot of mathematical analysis, I always write a very detailed supporting information so that anyone can follow the steps which were not actually described in detail in the paper, right? Sometimes they even attach Excel sheets that this is what how we analyze data, so that for reproducibility sake. And that's a common complaint, and in every conference I complain that any research paper, especially dealing with chemometrics and the mumbo jumbo equations and so on, if you are not sharing the code or the implementation details, that paper is useless. When I review papers, as a when editors send it to me, I usually say to the authors, can you please share the code? And actually majority of them do, but sometimes like I've seen, I mean, I'm talking about scientific ethics, like sometimes it happens that people have intentionally introduced mistakes in the code. I've seen that once or twice. So, and I even asked AI, I said, maybe I'm doing it wrong, but AI said, no, this function is not compatible the way it has been added in MATLAB or something else. And it was published because not everyone can test your code and so on. Following that strategy, whenever you see any paper, like you talked about the Gaussian test, we have a full Excel sheet with that paper. It's available in the Journal of Chromatography, and you can download free. There's no cost associated with it, and you can try your own data. And it works on a single peak at a time. You cannot upload a full program. You have to analyze one single peak at a time. Little bit primitive, but somebody can always improve it. And the derivative test is also easy. It's there, but if somebody wants to do it, you can do finite difference methods. And again, what I also should emphasize is that if you ask AI, even AI will tell you that how to do it in Excel. So use this technology, which was not available when I was a student, or we really had to ask people or go to library, ask on different forums. So yeah, I still have to sometimes ask on different forums when I cannot find an answer. Check the supporting information files.
I'm sure for most of us, it feels like this technology wasn't around even 5 weeks ago.
That's true. That's true. I mean, I feel like I said, "Oh wow, if I wish I had this," but I also feel happy that it was not in my time, because I would not have learned the hard way. I would not have interacted with people, or I would have not. I made good friends like spectroscopists and mathematicians. Otherwise, AI would be my friend. So it's a useful technology for sure.
There's certainly some large spreadsheets I've maintained for years that I've gradually phased out because I'm able to use more tools where some of those formulas are done in the background, and it
Exactly.
it is one of those. I understand what's
Right.
happening, but you do appreciate at some level the work you put into doing it
Yes.
with a more
Yes.
manual
Yes.
approach.
I mean, the nice thing about AI is that it does not get angry if you ask too many questions, right? With humans, if I don't understand something, probably they'll get annoyed. They'll stop answering my email or something like that. There's a limit, to human patience. AI has infinite patience, and you can ask as many times as you want. But be cautious, again, as they always say at the end in gray letters. ChatGPT can produce wrong answers. So check check the
Totally.
reliability of those answers as well.
And part of my hope with having these conversations is to make the content a little more digestible with people talking about it, because certainly I review a lot of research papers that
True.
um, look a lot like what you described earlier. So it is a challenge in some
Even
ways
I
making.
cannot
Hmm?
follow paper. Even I cannot follow certain papers, and then with so much time spent in this field, and it's so difficult because they haven't shared the exact details.
Totally.
Yeah.
I know this is a broad question, but
Mhm.
how do baseline correction and denoising really work? And why should researchers, students learn these concepts, especially if they're new to computational methods?
Mhm. So noise and signal problems are almost completing a century. So in 19, the concept started in 1925. So it's 2025. So around that era, so people wanted to communicate, and there was noise. That's where it comes from, right? In the communication. Thankfully, we don't have noise here. But imagine if you were in 1925, you would have some signal, some video, plus noise. So denoising and getting rid of noise is a 100-year-old problem. I was reading one old German translation, and one of the physicists said, "I wish, I mean, the dream of man." It was 1918, I think. I'm forgetting the year. Pardon me if that is wrong. The dream of man, trying to hear the grass grow, will come true. You see, so it means zero noise. But noise will be a part of any measurement. So any measurement you make, there will be noise, regardless of chemistry, regardless which instrument you're using. There will be noise. So we should study how to denoise that data. People also think there's one common misconception that noise is separate from a signal, like the acquired signal. Noise is a part and parcel of that signal, and it is your discretion what you consider as noise and what you consider as a signal. Okay. So coming to the actual question, we should learn how to denoise and do baseline corrections. Is that for in order to understand noise, we have to look at the data in another domain, which is that we should look at the data in frequency domain instead of time. If you remember, Fourier was a very famous mathematician. He said that any time domain function or any shape can be expressed as a sum of sines and cosines. That was a breakthrough idea of his time, but nobody believed him as usual. It took him a while to convince people that's doable. For example, I can tell you that if you add the right number of sinusoids, you can literally cancel the oscillations elsewhere and you'll be left with a single Gaussian. I showed it one time and people were, wow. So the idea is that when we look at the data in the frequency domain, we know that noise has a higher frequency than our signal. For example, if you remember, look at a chromatogram, you have a noise, and a peak, and then noise again. So our peak is a slow frequency component of the signal, and a noise is moving faster than the peak. So when you look at the data in the frequency domain, you can isolate the noise from your desired signal. So you can cut it off, chop it, and then transform it back into the time domain, and then you have a denoised data. So denoised chromatogram. You can do this in time domain as well, but I want to show why we are when we talk about high frequency, what is that frequency? The frequency of the sinusoids we are talking about. That's what we are chopping in order to denoise data. And similarly, baseline correction is a little bit more advanced. It's slowly varying noise. So there are more advanced methods, and you need to use optimization theories to get rid of that. Simplest one is that you fit a polynomial in the baseline region and get rid of subtract that polynomial from your chromatogram, and then your chromatogram is baseline free. Noise is a bigger problem than the baseline. So I have spent more time in denoising rather than correcting baselines. Again, AI is really good at it. So if you ask baseline, if you give those questions, it will generate really good mathematical answers. And they're correct. I've tried them.
And you can ask it as many times as you want.
Exactly, exactly. Sometimes I make ChatGPT to write a code and then I ask it again after a day or so, can you recheck? And it finds more mistakes in its own code. Never happy with its own work.
What advice do you have for undergraduate chemists who want to stand out or just succeed in general in analytical chemistry and chromatography research?
Very good question. Because if you want to excel in analytical chemistry, I say there are four pillars of analytical chemistry. One is chemistry itself, but the other ones which majority ignores is physics, scientific computation, and mathematics. Therefore, that's the four pillars of analytical chemistry. So you must, if you really want to excel and really want to do creative work in analytical chemistry, you should have exposure to all these four areas. I may be a very good mathematician, but zero in chemistry, I cannot be a good analytical chemist. I am a very good chemist, but and mathematician, but my physics is poor. I cannot understand how instrumentations work. Because in instrumentation, you have physics, you have electronics, you have some data processing, which is scientific computing, like denoising and baseline correction will come under the umbrella of scientific computations. For example, just talk about HPLC detector, right? What is the light source there? If we do not know decent amount of physics, we will not be able to explain why we need to use a deuterium lamp or a xenon arc lamp. Like, why are we using these sources? How are we selecting wavelengths? What is actually happening? There are diffraction gratings inside, diffraction gratings, physics, right? So when you are setting method parameters, you are asking, okay, select this reference wavelength, or this should be your bandwidth. What is this? Pure physics again. So if you do not know these terms, yes, you can become a very good technician, but you will never be able to do creative work in analytical chemistry without the knowledge of physics, mathematics, and scientific computing. So this is sad, like that majority of the instrumentation is becoming a black box these days. And even if I try to ask something, like I saw some phenomena in a major manufacturer's detector, They won't tell me. I asked them so many times, and the answer was, I mean, vague at best. So, like, black box thing is happening. But in older times, like 80s and 70s, people would build their own instrumentation, right? So that was a great era. As I said, that's the golden era of US science, when you had the best scientists, and building everything in your own lab. You knew what is happening. Nowadays, some part is coming from China, some part is from Germany. Nobody knows. Software is made by another company, and so on. A lot of black boxes. So that is hurting analytical chemistry, in my opinion.
And that's actually the story of Organimation, my
Oh, okay.
company, as far
Hmm.
as the founder was a PhD chemist,
Hmm.
but he did have a mechanical engineering background. So there was this evaporation challenge he had in doing concentration and invented the first multiple sample evaporator on the market. So that was
That's pure
really our,
engineering too.
yeah, that's really our story. But yeah, there was certainly an era where that's how a lot of the newest devices came to be. It was the people who actually doing that work who had that need,
That's true.
seeing through a solution.
That's true. Science has expanded a lot. You cannot be a master of all these days, right? I cannot know everything, but you can be an expert in a narrow area, and you should excel there. It's overwhelming actually these days, that how many things should I also learn Python, or should I also learn MATLAB, or should I know scientific computing? It is overwhelming these days for sure. There's so many things, but the idea is narrow your focus and then excel in that direction. People will slowly recognize you in that area.
Absolutely.
Yes.
So this has been a great introduction to a lot of these major topics
Mhm.
regarding peaks. Was there anything else you wanted to discuss today that we didn't cover?
I think recently I attended a session for fresh postdocs, and the main thing which I emphasize, that if you're following science, there's not enough money there. So if you want to study physics, mathematics, or chemistry, you need to have a certain level of passion and the level of sacrifice if you really want to study science. But like, you won't get money right away if you get like graduate with a bachelor's degree or a master's degree or a PhD. It will be a slow build up. So it's not a area where you can suddenly become rich overnight. So keep that in mind when you're studying pure sciences.
That makes sense.
Yeah.
I think this has been a great conversation. I was really excited to focus on this subject just in general because it applies to basically all the work that everyone's doing that I'm talking to, where
Mhm.
most of these interviews have been someone's done this project and we're discussing it from,
Mhm.
their workflow to what was the motivation to what were the findings, where are we going from here, where this was like a really solid fundamental introduction to a topic that is relevant to literally everyone doing chromatography. It all comes down to the
Sure.
peaks.
Thank you. It was nice meeting you as well.